Okay, so we've talked about ways to see melting aloft, ways to see transition areas, but let's talk about how do we just spot when there's heavy snow and maybe when there's really heavy snow. How do we do that? We want to see two things to get us heavy snow or really heavy snow, where we're just getting those rates 2-3 inches an hour. They're really good stuff. A, we want to see lots of ice crystals growing aloft, because we need lots of snow to form aloft to come down to the ground. And then we want to see a process known as aggregation, which is this clumping of these crystals into those big, fluffy snow aggregates, those things you see that hit the ground kind of, sometimes they get so big they can kind of explode if they hit your windshield, where you get all those crystals together, maybe dendrites, things like that, that clump together and then come down to the ground in a big snowflake. I reference specific differential phase now for one reason with the crystal growth aloft, and we mentioned this before, but it's something you can use, and there's been some recent research on it as well that's identified this signature aloft in your favored crystal growth region for really heavy snow. If you recall from the first module, we mentioned there's not a big range to KDP when dealing with crystal growth. It's somewhere in the range of about 0 to 1 degrees per kilometer. It's a small range, but subtle increases in it can mean a big difference in terms of how many crystals you're growing aloft and in terms of your snowfall rates. That small range of KDP values with ice crystals growing aloft can mean a big difference in terms of how many crystals you're growing and perhaps how heavy snow is. So what are we talking about? Let's imagine we're looking in the cloud and we want to look around what we know to be the heights for about the -12 to -18 degrees Celsius layer. That's where we tend to grow our most we tend to efficiently grow ice crystals that are nice and airy, have a branch structure, dendrites for instance, where these snowflakes don't need much moisture to grow these big shapes that can clump together and can stack up really quickly on the ground. So it's where we're most efficient at creating our very heavy snow. That's why we want to look in that layer. So we will, like magic, grow our crystals. We have some dendrites here, those nice pretty branched ice crystals. And also let's imagine we have some hexagonal plates that are growing as well. They can tend to grow at some colder temperatures as well, and they tend to contribute to the signature we're about to see here. So we send in our radar beam. We have our vertical polarization, we have our horizontal polarization in the blue, and similar to when there's a lot of rain, just not at the same magnitude, if we have ice crystals that tend to sort of float or orient themselves in the horizontal as they slowly descend towards the ground, the horizontal polarization just runs into more stuff. It runs into more ice than the vertical polarization does. So similarly, our horizontal polarization is going to slow relative to the vertical polarization. And that difference is that value in KDP. So higher KDP means that our horizontal polarization is starting to lag progressively behind our vertical polarization. So if we have a greater number of crystals, that increases our KDP. So you call that crystal growth? Let's really grow some crystals here. Some light to moderate snow though, KDP generally. And these are not hard and fast numbers, but there's a little bit of gray area, at least on either side of them, generally in the range of about 0 to 0.2. And so you're already seeing how subtle of a range it is if we're talking 0 to 0.2 degrees per kilometer. Let's say we're getting to heavier snow, 1+ inch per hour. KDP can be somewhat higher, maybe 0.2 to about 0.4 degrees per kilometer. And again, this is all up top where we're watching our ice crystals generate in this -12 to -18 degrees Celsius range. And then if we start to get to really heavy snow associated with lots of ice crystals growing aloft, we're looking at KDP, maybe that's about 0.4 to 0.5+ degrees per kilometer. So we're starting to increase those values even more. But remember, we highlight it in white. We got to look at higher elevations on radar. That's where we can observe crystals grow efficiently. We look at an example from a big snowstorm they had about a year ago in Washington, D.C., or across the mid-Atlantic, really, and D.C. was one of the areas infected. On the left, reflectivity. On the right, correlation coefficient. At this time, they're getting generally moderate snow across the area. Correlation coefficient is nice and high, so there's a lot of snow, pure snow across the area. But we want to look up top, where we're growing our ice crystals. So we tilt up to 3.4 degrees on the radar. And we look at KDP here, and we don't see, although, again, we're dealing with a pretty small range that we'd expect those values to be in about 0 to 1. There's no noticeable enhancement in our KDP values. It's all pretty close to 0, just slightly above 0. And you could be sampling, too, if you had GR open or some other radar program open to see what those actual values are. There isn't really much of an enhancement of KDP aloft, looking 10 to 20,000 feet above the ground in that ice crystal generation region, where we're just starting to see some enhancements of reflectivity. So let's head south towards an area we knew there to be better ascent, to see what KDP looks like down there, where maybe we're growing ice crystals a little bit better. So we'll go down farther south in Virginia, down to Wakefield, Virginia. And now we're looking still at 3.4 degrees, but you'll notice sort of on the southern extent here, we're lighting up an area. Look at those enhancements in KDP, though. Much higher values, relatively speaking, for ice, where we're dealing with more in that 0.5 to even 1 degree per kilometer range. If we were dealing with convection, warm season, it's not really a notable enhancement. But for winter weather, especially in this range up towards our ice crystal generation zone, that's a very noticeable enhancement. And so what that's telling us is we have lots of good ascent down there that's helping to grow a lot of ice crystals very efficiently. If that's moving north and I'm in DC, maybe my snowfall rates are about to increase over the next few hours as this moves north. So this better KDP signal can indicate better ascent and crystal growth that may be approaching the region. We take a cross-section, as you saw that line right there. Here's reflectivity. You can see up to about 20 to 30,000 feet. And there's that notable enhancement in KDP right here. Now this farther down is due to melting. And so yeah, maybe here they're not dealing with snow reaching the surface, but still we can get an idea of how the ice crystals are being generated, how well they're being generated aloft. And if I'm somewhere where the thermal profile does support snow, and this is coming at me, well, maybe I need to be aware of an uptick in snowfall rates over the next few hours. So we highlight that area where we're seeing those nice KDP values, again, in that sort of negative 15, in this case, negative 15 to negative 20 degrees Celsius range. So near ecotop, but again, you're generally thinking somewhere in that negative 12 to negative 18, even negative 20 degrees Celsius range, where you can see those dendrites and even some of those plates start to grow. So here we have at least those dendrites and again, some of those hexagonal plates growing up top. What we're going to do now is look at a loop of data from Washington, D.C., and we're looking up top again. You can watch as snowfall rates at Baltimore and at Dulles increase through the next several hours. And what you see come out of the south there, at least, are some of those higher rates approaching the region. And they match up nicely in terms of how we see our snowfall rates increase. They went from maybe a half an inch to an inch an hour to 1 to 2+ inches an hour as we see that better ascent and that better crystal growth as indicated by our higher KDP aloft, looking in our ice crystal generation region. And that was where we saw those snowfall rates increase, and temporally that's where we saw it, generally after about 6Z across the DC and Baltimore areas. So we'll watch the loop one more time that we've explained it, and we'll see what happens here. So watch again from the south as we get those higher KDP values moving in, and then you can watch with the observations too, at least at Baltimore and Dulles, how we go from light to moderate snow to mainly moderate to even heavy snow, and even farther afterwards, really heavy snow as the storm really started to take shape, and that strong ascent was leading to really good ice crystal growth aloft, where it's efficiently growing them in, as observed by that higher KDP. So check mark on lots of crystals growing aloft. That's one. Now we talked about the other part, aggregation or clumping. We want those ice crystals, if they clump together and they're very airy then in sort of that clumping or that aggregation, they can stack up even faster, and that can also enhance our snowfall rates. How do we observe that? Well, we go back to looking at LWX, the radar from the region. We highlight an area of higher ZDR, again looking at 3.4 degrees. Well, what's that telling us at least? We look at what we know from ZDR again. If we have lots of crystals growing, or we have crystals present, and they're not aggregated, they're just sort of these pristine crystals generated aloft in that ice crystal growth region we want to look at, they tend to have higher ZDR. We can see that sort of in that wider horizontal extent than the vertical extent. So we got a really fancy GIF here. I spent a lot of time working on this. So as our crystals are growing aloft, they're unaggregated. And then they fall and you get new crystals to form, and they're going at different velocities, and if the thermal profile supports it as well, they clump together, and that's known as the snow aggregate. What happens when they start to clump together is due to the airiness of it, and then some of the shape as they're kind of tumbling and fluttering about. ZDR drops as you get the aggregation process. So that decrease from high ZDR to low ZDR through that depth shows you something about how aggregation's ongoing. And those fluffy aggregates can enhance snowfall rates even further. So let's take a cross-section through that high ZDR that we witnessed before. So there's our cross-section. We have reflectivity increasing towards the ground. And notice we have our high ZDR and then our low ZDR as we get closer to the ground with our cross-section. We overlay the image of our growing snowflakes, and that's what happens. Initially, where the snowflakes are growing, or the snow crystals, the dendrites, and maybe some plates too mixed in and other crystals, you get that high ZDR. And then as they aggregate, our ZDR tends to decrease due to the presence of snow aggregates. You also see reflectivity, this is also part of it, increases. While we have our growing crystals up here, as they start to clump together, you get these sort of really big, relatively speaking, really big snow aggregates. And these clumps of snow to radar tend to send more energy back than just the individual crystals themselves. And so because of that, the aggregation process will increase reflectivity closer to the ground. So this is a nice signal of aggregation. One other thing we can look at, though, correlation coefficient. We see some subtle decreases aloft where perhaps we have different crystals growing, the different shapes and structures to them tend to look a little more diverse to the radar, so that drives correlation coefficient down ever so slightly, maybe some specks of 0.95 or 0.96, something like that. But the clumps of snow, because of their airiness and sort of the structure of them, we won't go too far into the scattering properties and how that works, at least in terms of our radar variables. What you need to know is that the clumps of these snowflakes into these bigger aggregates tends to look very similar. They all look similar to the radar. And so if they all look similar to the radar, it thinks there's not much diversity there, and that drives correlation coefficient back up. And so you tend to see this nice increase when you get aggregation in terms of correlation coefficient as they fall down to the ground and aggregate. So check mark on our aggregation. We have that as well. So snowfall rates, we get them maximized by two primary processes. We want vigorous crystal growth aloft. We see that with enhanced KDP near that range around negative 15 degrees Celsius. And we want them to aggregate too. So we get that extra fluffiness and they stack up really fast to increase the snowfall rates. We'll see that with decreasing ZDR and increasing reflectivity and correlation coefficient as we look closer and closer to the ground. And so those are the two processes we want to look at when dealing with dual polarization data and heavy snowfall. With that, we'll wrap up that segment.